Network analysis, Thevenin's theorem. Thevenin's theorem, it states that any two-terminal linear bilateral network containing a number of voltage sources and resistances can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistance RTH and load resistance RL, where VTH open circuit voltage VOC between terminals A and B, it is also called as Thevenin's voltage. RTH, the equivalent resistance of the network as seen from the two terminals A and B, with all other voltage sources replaced by their internal resistances. It is also called as Thevenin's resistance. RL equals any load resistance. Thevenin's equivalent circuit is nothing but a combination of Thevenin's voltage source VTH in series with RTH, Thevenin's equivalent resistance, which is similar to a particular voltage. Step 1. To determine the current through load resistance RL, temporarily remove the load resistance RL from terminals A and B as shown in the figure. Step 2. Find the open circuit voltage VOC, which is also equal to VTH, between the terminals A and B by keeping all sources in their original position as shown in figure B. Total resistance R equals R1 plus R3. Current through R3 I3 equals V by R, which is V by R1 plus R3. Voltage across R3 VTH equals I3 into R3, which is equal to V by R1 plus R3 into R3. Determination of RTH. Find Thevenin's equivalent resistance of the network as seen from the terminals A and B as shown in the figure C by replacing the voltage sources by their internal resistance, or short circuit if its internal resistance is not given, and current sources are open circuit, which is as shown in the figure. As R1 and R3 are in parallel and this combination is in series with R2, therefore RTH is equal to R1 parallel to R3 plus R2 is equal to R1 into R3 by R1 plus R3 plus R2. Step 4. Draw the Thevenin's equivalent circuit by replacing the entire network by a single Thevenin voltage source VTH in series with Thevenin's resistance RTH as shown in the figure. Step 5. Connect the load resistance back to its terminals A and B. View figure E where it is removed. Step 6. Determine the current flowing through RL by applying Ohm's law, that is IL equals VTH RTH plus RL. Step 7. The potential difference across the load will be VL equals VTH by RTH plus RL into RL. Problem. Obtain Thevenin's equivalent circuit with respect to the terminals A and B of the network as shown in the circuit. Determination of VTH. Applying KVL to the closed loop for the figure B, we have 10 minus 5i minus 10i minus 5, which is equal to 0. 5 minus 15i equals 0. 15i equals 5. Therefore, I is equal to 5 by 15. VTH equals VAB minus drop across 5 ohms. 15 minus 5i equals 10 minus 5 into 5 by 15, which is equal to 8.33 volts. Determination of the RTH. RTH equals 5 ohm parallel with 10 ohm, which is 5 into 10 by 5 plus 10 is equal to 50 by 15, which is equal to 3.33 ohms. Thevenin's equivalent circuit is as shown in the figure. Thank you.